Okay, so now that we have the network itself, I'm just gonna put copy this part over here and put in the previous cell. Okay, just to put everything together. Okay. Well, you don't need to show the graph. I'm just showing it just for as a well, just as a proof that we constructed the graph we are expecting. We want to. Okay. I should emphasize that this data is from the book. Okay. The idea here is not to say that the vaccination or any vaccine is harmful to people. Okay. Those are not my conclusions. This is basically the intent here is just to implement what is on the book. Okay. I'm not saying anything about that. I'm not saying that the vaccines in general, they are harmful to people. Okay. So coming back to our Bayesian network, now that we have the graph, it's the time where we are gonna implement, we're gonna put the data over there. Okay. So the most important part for us is this second part over here. So suppose out of 1 million children, 99% are vaccinated. Okay, so this is exactly what we have over here at the top. Okay, so those are two pieces uh, of text taken from the book. Okay, so 99% of are vaccinated and 1% are not. Okay, so vaccine, for the vaccine verbal, we have true and false, no, yes. Okay, and we are going to insert the data over there. At this point, doesn't matter this number 1 million children. Okay, it doesn't matter at all. What we are looking at here is the proportions. Okay, so let's fill the CPT. CPT stands for conditional probability table or node probability table. Okay, so our initial CPT, it's the vaccine CPT of related to the verbal V as we discussed here. Okay, so we call our Bayesian network, our verbal BN we created over here. Okay, BN dot CPT, the verbal we want to set. Okay, and we can use the method. There are a couple of ways of doing that, but for this, I'm going to use the method fill with, okay, where we should pass a list of numbers, and this list will define how many states, how many bars. If you see a conditional probability table as a bar plot, how many bars we're going to have over there. Okay. For this verbal, I'm going to consider the first number. We should put two numbers over here, right? I'm just going to put 0, 0. Okay. It's totally wrong, but just to exemplify. So the two numbers we are going to put, I'm going to put here as N1 and 2 will correspond to no and yes. Okay, and obviously we are talking about the vaccine. Okay, so this is our verbal B. Okay, so this is our assumption. This is how we construct our conditional probability tables for this verbal. So no to vaccine, let's go back to the data. It's 1%. And 99% are vaccinated. So no vaccine, this is 1%. So we should put 0.01. And yes, to vaccine, this is 0.99. Okay, those are basically probabilities, so they should sum up to 1. Okay, so that's why we have this. If you don't sum up to 1, well, something is wrong. You should review your module. Okay, so this is the first CPT. The second CPT, we can take the reaction node over here, right? So I'm just going to copy the first part over here just to speed up a little bit. So this is the reaction. We should specify the verbal, of course. And I'm going to use in a different way just because we have reaction as a child node of vaccine. Okay, so that means for reaction we have two possibilities. Well, for reaction, we have two possibilities. One is vaccine true, and another one is vaccine false. So how can we specify that? Okay, and for vaccine true, we have reaction true and false. You know what I mean? So we should insert 4 numbers in total. Okay, so the first pair of numbers we're going to insert is for vaccine false. So we can specify just like that. Okay, vaccine 0. Okay, so this is false for us. This is our assumption. Okay, and then we should fill the 2 numbers for that because again, this is reaction. Okay, so this is our variable R. We are going to have 2 numbers as well because this is a binary variable. Okay, will be no and yes, exactly the same structure as vaccine. Okay, so we should put 2 numbers here. And then next, just gonna copy and paste here. Next, we need to set another pair of numbers that correspond to the situation where vaccine is true. Okay, so let's take a look at the data. If a child is vaccinated, he or she has 1 chance in 100, that means 1% of developing a reaction. So if we take a look at vaccine true, so this is the number we are looking at right now, okay? And the reaction would be the second number over here, right? So according to the data, we have, if the child is vaccinated, so the vaccine is true, he or she has 1 chance in 101% of developing reaction, okay? So 1% to develop the reaction. So that means 0.01. That is the 1% of developing the reaction. So that means 99% of not developing any reaction if that child was vaccinated. Okay, so vaccine equals to true. We are taking the data from the text. That's it. Okay. So let's see, we have the vaccine 100%, 1% of developing reaction. Okay. And then I'm just gonna go through the text. So reaction has 1 chance in 100, so 1% of being fatal. So here we are talking about the reaction variable. Okay. Reaction variable and the fatal variable. So if that child had a reaction, there is 1% of probability of being fatal. Okay, so how can we describe that? Fatal, it's about our variable death. This is our node D in our graph. Okay, so for that, since D is child of reaction and smallpox, we have 4 situations over here, just because of the structure of the network. Okay, let me just copy this part over here, and we can update with that. I will leave some things empty for now, but as soon as we know the data, we read the data, we can fill the gaps. Okay, so this is the def variable. So this is our node D. We have 2 possibilities. Okay, just because D is child of R and S. So one possibility is reaction, okay, false, and smallpox is false. Okay, and we should put 2 numbers over here. Okay, I'm just gonna leave for now. I'm gonna copy it again just to copy and just to have the 4 possibilities we should have for this CPT. Okay, for each of those lines, we should specify 2 numbers because those 2 numbers correspond to def, true, and false. Again, the same structure we had before. So the first number will be no for def, the second number will be yes for def. Okay. So death reaction false, smallpox false. Then the next possibility is reaction false and smallpox true. The third possibility is reaction true and smallpox false. And the last one is reaction true and smallpox true. True. Okay? So let's go back to the text. Reaction has 1% of being fatal. So that means if the child had the reaction, okay, and according to the text, it's saying about the child being vaccinated, right? So it was he or she was vaccinated, okay, and he or she developed the reaction. Okay, so this corresponds to the, and didn't mention anything about smallpox yet. So let's put the 100%, the 1% over here. Okay, and the first number is the 99%. Okay, so here we are saying 1% of probability of this child die if they had a reaction, and they didn't have smallpox. So basically, they died from their reaction to the vaccine. Okay? On the other hand, he or she has no chance of developing smallpox. So that means if the child was vaccinated, they are not going to have smallpox. So this is about our smallpox vaccine, verbal, our verbal S, exactly the same structure as before. I'm just going to copy and paste to make it simpler. We have two possibilities only, just because smallpox is child of vaccine. Okay. So our verbal is smallpox, verbal S. We have vaccine false, vaccine true. Okay. Come back to the text. On the other hand, has no chance of developing smallpox. So that means the child is vaccinated, no chance of developing smallpox. The child is vaccinated, smallpox, no for smallpox is going to be 100%. Okay, and 0% for developing smallpox. That means if the child is vaccinated, no smallpox at all. Okay. Meanwhile, if a child is not vaccinated, he or she obviously has zero chance of developing a reaction. Okay. So that means developing a reaction is going to be a 0% chance if the child is not vaccinated. Okay. So reaction no will be 100% and 0% for yes, just because in this situation we are considering vaccine equals to false. So that child was not vaccinated. Okay, so no vaccinated, no reaction at all. Okay. Next, it says, but, right? So meanwhile, if a child is not vaccinated, he or she has 0% chance of developing a reaction, but he or she has 1 chance in 50, so that means 2% of developing smallpox. Okay, 2% of developing smallpox. So going to our verbal smallpox, the child wasn't vaccinated, right? So 2% of developing smallpox, so this is our 0.02, and 0.98 of do not develop smallpox. Okay. Yes, code is saying wasn't closed. I don't know why it's still insisting on that. Okay, 150% of developing smallpox. Finally, let's assume smallpox is fatal in 1 out of 5 cases. Okay, 1 out of 5 cases. So here we are considering the situation where we have 20% of probability of smallpox being fatal. Okay, 20% probability. So we are considering this variable over here. Okay, reaction 0 is smallpox true, and again, this is how I interpreted the data from the book. Okay, so 20%, and we have 0.8% over here for death equals to false. Okay, so 20% death true if the child had smallpox, and um, reaction 0 and 8% for no death under these conditions. Okay, so read the text, and we can assume some other numbers here as well. Like, for example, death, if the child didn't have any reaction and neither is smallpox, well, the child's not gonna die, right? So we can feel that. It's kind of implicit over there, okay? And here it's a very interesting case where we consider the situation where the child had reaction. So obviously he or she took the vaccine and they had smallpox. Okay. So what is the probabilities of that? So what I did here, it's basically we are considering the death of that child in case of they having both reaction and smallpox. So basically what I did was to sum up those numbers over here. So that means 0.21% okay, of death. And on the other hand, we have 0.79% of probability of not death, to not die. Okay, so this is it. We filled all the CPTs, all the numbers of our Bayesian network. So let's run this code. Okay, so just run. Okay, although Visual Studio Code is still insisting having these brackets closed, but everything, as you can see, it's right. Okay. PyAgrum has a very interesting feature where you can take a look at some variables or some CPTs after you build them. Okay, so let's take a look at the CPT, for example, the smallpox one. Okay, so you can type just bn.cpt. So it's going to return to us the graphical representation, the table related to the smallpox variable. So it shows all the 4 numbers we inserted over here. Okay, so this is can be actually kind of a sanity check where we check the numbers you just input over there. Okay, one thing that I noticed using PyAgrum is that if those numbers they do not sum up to 1, it's going to show in a different color other than green and red. Let's say if I have here 0.1. Obviously, we know this is wrong, okay? It's gonna accept the input, and then when you plot, you see it's not in green and red anymore. So that means something is wrong with this data, okay? And since we caused this mistake, we know why, okay? But this is a very interesting thing. So look at this table, and we can come back to our graph for smallpox. We know smallpox is child of vaccine, right? So that's why we have the first column over here, the vaccine. So vaccine false true, smallpox false true. Both are binary variables, and the numbers we just inserted. Okay, and we can take a look, of course, at other variables as well, like the variable d, for example. So how does it look like? So let's run it. So there we go. D, looking at the graph, it's child of reaction and smallpox. So that's why we had to insert 8 numbers in total, right? Just to consider all the possibilities of the parent variables over here. And that's why what we see when we are plotting our CPT over here. Okay, so we read the text, we insert the data over here, And that means our Bayesian network is complete. So how can we see the Bayesian networks? Because we saw the graph, we can see individual CPTs one by one as by using the bn.cpt and specify the variable. But is it possible to show everything together? Yes, it is. PyAgrum has the method show inference from GNB. GNB is what we imported over here at the very beginning, but we didn't use it so far, okay? GNB.show inference. We are not going to do any inference right now, but we are going to use this method just to represent our, just to see our Bayesian network, okay? So show inference, it is expected to have two inputs. One, it's the Bayesian network itself. So the Bayesian network we specified at the very beginning, and we then fill the CPTs. And the next variable is the evidence. So this is the EVS variable. Since we are not going to set any evidence right now, we can leave empty curly brackets just like that. Okay. We are not doing inference. We are just asking to PyAgrum to show us the Bayesian network that we constructed before. Okay. So it's taking a while, and there we go. So here we see all the variables. It's exactly the same structure we had before over here, okay? But now we are looking at not the CPTs itself, but the probabilities of every single state per variable. And PyAgrum also calculates the mean value and also the standard deviation, okay, for every single variable. Okay, so basically those numbers we see over here is the sum of what we have specified for every single state, every single piece of data we inserted over here, okay, for every single variable, okay?